Today I will talk about some basic concepts in graph theory. Graph theory is a very interesting field because it has many important applications. You can use graph as a model. So here are some areas where you can apply the concept of graph theory: transportation, road maps, computer, electrical, etc. And you can also use the notion or the concepts in graph theory to solve problems, certain problems. For example, assigning people to jobs, arranging weddings, finding appropriate roommates, etc. Another is that you can use graph theory again for scheduling and making timetables, and you can also apply again the concepts of graph theory in biology, chemistry, geometric polyhedra, chip design, ecosystems, and so on. Puzzles and games even. So first off, we define what a graph is. Basically, a graph consists of points called vertices and lines called edges. So as you can see here, this figure on the right, this is an example of a graph with 1, 2, 3, 4, 5, 6, 6 vertices and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 edges. So again, these points here are your vertices or vertices. And the lines connecting two vertices are what we call as edges. So this line which connects these two vertices is called an edge. So we normally write G as this pair, VE, where V is your non-empty set of elements called vertices, or this is also called your vertex set of G. And your E here is the set of pairs of elements of V called edges. So your E is called the edge set of G, your V is called the vertex set of G. So your V is the set of vertices in your graph, while E is the set of edges in your graph. Okay, so in this example, try to look at this figure on the right. The vertices are labeled V sub 1, V sub 2, V sub 3, V sub 4, V sub 5, V sub 6. So since there are 6 vertices, okay, and here are the vertices that was I've mentioned. So your vertex set is now the set containing these vertices, these points here in this graph. And your edge set is the set containing the edges. So in this case, you also have the graph is also the graph's edges are also labeled. So you can just write these edges here in your edge set. So you have E sub 1, E sub 2, E sub 3 up to E sub 7. So as you can see, there are 6 vertices and 7 edges. So the number of vertices is what we call as the order of your graph. Since we name our graph G, then the order of G is 6. Again, the order of your graph is just the number of vertices in the graph, while the size of your graph is just the number of edges in your graph. So in this case, you have 7 edges, right? So the size of G therefore is 7. And we say that two vertices, are adjacent if there is an edge connecting the vertices. So for example, vertex 1 and vertex v sub 1 and vertex v sub 2 are adjacent vertices because there is an edge e sub 1 connecting these two vertices. Another example, vertex v sub 6 and v sub 2 are also adjacent because again there is an edge connecting the two. Vertex v sub 4 and v sub 2 are not adjacent because there is no edge connecting the two. V2 and V5 are also not adjacent. Multiple edges. What are multiple edges? So these are edges that connect the same vertices. For example, V sub 5 and V sub 6, they are adjacent vertices because there is an edge connecting them, say, say E sub 7. But notice that E sub 6 is also connecting these two vertices. Same with E sub 5. So as you can see, there are three edges connecting the same pair of vertices. So we call these edges multiple edges, from the word multiple. And then we also define what a loop is. A loop is an edge which connects itself. Okay, so this E sub 4 here, this edge, connects V sub 3 to itself. And a multigraph is a graph which contains multiple edges, just like this one. This is a multigraph. A pseudograph is a graph which contains a loop. So this is an example of a pseudograph. And a simple graph is a graph which does not have a loop and does not have multiple edges. So this is an example of a simple graph. An empty graph is a graph with no edges. So as you can see, all vertices only. And a trivial graph is a graph which consists of one vertex only. So this is your trivial graph here. And then next we define what a degree of a vertex is. A degree of a vertex is the number of edges incident to it. So I haven't defined what um, when do we say that an edge is incident to a vertex. So we say that an edge is incident to a vertex if it is connected to that vertex. If how do I say that? For example, your V sub 5, E sub 7 is incident to vertex V sub 5 because E sub 7 is connecting V sub 5 to some other vertex. So E sub 7 is incident to both V sub 5 and V sub 6. Another E sub 2 is incident to V sub 6 and V sub 2 because E sub 2 connects these two vertices. So to obtain the degree of a vertex, you just have to count the number of edges incident to that vertex. For example, the degree of V sub 1 is 1 because as you can see, there is V sub 1. Yeah, V sub 1 is here. So there is an edge incident to it, one edge, E sub 1. The degree of V sub 2 is 3. Why? Because there are 3 edges incident to it. The degree of V sub 3 is 3 because you have three edges incident to V sub 3. So you have 1, 2, 3. So you count the loop twice. V sub 4, the degree of V sub 4 is 0 because there is no edge incident to it. The degree of V sub 5 is 3. You just count the number of edges incident to V sub 5. And lastly, the degree of V sub 6 is 4. 1, 2, 3, 4. Now we say that a vertex is odd if its degree is odd. Okay, as you can see from the obtained numbers here, the degree of V sub 1 is 1 and 1 is odd. Therefore, V sub 1 is an odd vertex. Another, the degree of V sub 2 is 3 and 3 is odd. Therefore, V sub 2 is an odd vertex. Another, 3 is odd, so V sub 3 is an odd vertex. And V sub 5 is also an odd vertex. Now 0 and 4 are even numbers. Therefore, V sub 4 and V sub 6 are even vertices. An isolated vertex is a vertex which is not adjacent to any other vertices in the graph. So as you can see, V sub 4 is an isolated vertex. Its degree is 0. And then, as I have mentioned, graph theory has many applications. So you can use graph to as models, where the vertices will represent cities and the edges will represent flights between cities. Or you can use um, again, graph as a model where the vertices will represent people and then edges will represent pairs of friends. So there will be an edge between two persons if they are friends, no edge if they are not friends, and so on. Just like this example here. So you have webmaster's computer, we have the server. So since there is an edge connecting webmaster's computer to server, so this means something. And then, meaning there is a connection between them. And then you have um, Yankees, Mets. As you can see, these are the same graphs, but they represent different things. Here, these are teams of, I don't know which baseball, softball, I know, I forgot. You have your Braves, you have your Yankees, Mets, Giants, Cardinals, and White Sox. So White Sox and Braves, for example, there is an edge connecting these two if they played a match. Another is, I'll try to look at these cities here: San Francisco, Chicago, New York, Los Angeles. So, for example, Chicago to Dallas, there is an edge connecting these two cities because there is a flight between them. Something like that. So you can use graphs as models. They can represent relationships. Now try to look at this graph and analyze the relationship between the sum of the degrees of this graph and the number of edges. So as you can see, the degree of A is 3, the degree of B is 3, the degree of C is 4, the degree of D is 2, the degree of E is 4, and the degree of F is also 4. Now if you try to add those numbers, what will you get? And what is its relationship between the number of edges? If you try to count the number of edges, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9. Please recount. Yeah, 10 edges. 10 edges, and the sum of the degrees is 20. What do you notice? So there is actually a theorem for this, which states that the sum of the sum of the degrees of the vertices of a graph is twice the number of edges. So the sum of the degrees of the vertices is equal to twice the number of edges. So 2 times the size of your graph. And this is true. This is true for all graphs. And then you have here your corollary. This is a direct consequence of the theorem. In a graph, the total number of odd vertices is even. So there is always an even number of odd vertices. And then let's also cover some special graphs. You have the complete graph. These are very common graphs. Graphs that you will always encounter. One is a complete graph. This is a graph in which every pair of vertices are adjacent. So your trivial graph is actually a complete graph because this will satisfy the definition of a complete graph. Your K2 also is a complete graph because there are only two vertices, and as you can see, they are connected with an edge. This is your K3. This is your complete graph of order 3. So these two vertices are adjacent, these two vertices are adjacent, these two vertices are also adjacent. So every pair of vertices are adjacent. And this is your complete graph of order 4. So how do you make a complete graph? For example, you are to create a complete graph of order 10. So you just have to draw 10 vertices and then connect every pair of vertices. And then you also have your cycle, C sub n. Your n is greater than or equal to 3. So you need at least 3 vertices to create a cycle. So this is your C3, cycle of order 3. So this consists of n vertices v sub 1 to v sub n and edges v1, v2, v2, v3, v3, v4 up to vn, v1. So from the word cycle, So from this vertex to this vertex, there is an edge connecting them. And then from this vertex to this vertex, from this vertex to the first vertex. So there is a cycle. Another is your C sub 4. So from this vertex to that, this to this to this, and then this to that. So you have here a cycle of order 4. Now we define what a bipartite graph is. It is, we say that a graph is bipartite if its vertex set V can be partitioned into two subsets, such that each edge of E has one end vertex in one of its subsets and another in the other. For example, this is in this figure. This is actually an example of a bipartite graph. So as you can see, the vertex set was partitioned into two partite sets, into two subsets. So you have V sub 1 here and V sub 2. And an edge in your graph, an edge in this graph, connects one vertex from this subset and one vertex from the other subset. So you cannot see an edge connecting two vertices from the same set. Again, an edge will only connect vertices from different sets, from the two partite sets. Now, when do we say that a bipartite graph is a complete bipartite graph? This is usually the notation. This is the notation that we use for complete bipartite graph, K sub mn. So it's complete bipartite if every vertex of V sub 1 is connected to every vertex of V sub 2. For example, consider this graph. This is a bipartite graph. So this is your first partite set, and then this is your second partite set. So it's called, this graph is called K sub 2, 3, because there are two vertices from the first subset and three vertices from the second subset. This is complete. Why? Because every vertex from this set is connected to every vertex of this other set. So as you can see, this vertex is connected to this vertex, to this vertex, and to this vertex. And this vertex also is connected to these three vertices here. Another is this one. This is your case sub 3, 3, because again, there are three vertices from the first partite set and three vertices from the second set. And this vertex is connected to all the vertices in the second set. This vertex also is connected to all the vertices, and so on. So here are some examples of complete bipartite graphs. Okay, now what is a subgraph of a graph? Basically, it is a graph H. For example, you have a graph G equals this pair VE. So a subgraph of G is a graph H, which is equal to this a pair where your V prime is a subset of your V here and your E prime is a subset of E. Now, in particular, if the number of elements, if the vertices in H are all the vertices of G, then we say that that subgraph is a spanning subgraph. Again, if the vertex set of G is equal to the vertex set of H, then the subgraph is a spanning subgraph. Okay, so consider this graph G. This is your mother graph. And so here are some subgraphs. Here are some subgraphs, H sub 1 and H sub 2. As you can see, all the vertices in H sub 1 are from G, and all the vertices in H sub 2 are also in H. Again, you have your graph G here, and then here are some subgraphs, H sub 1 and H sub 2. So your H sub 1 is a spanning subgraph. Your H sub 2 is not a spanning subgraph because it does not contain all the vertices in G. Next, we have some graph representations. So you can represent graph as an incidence matrix or adjacency matrix. If you find, um, when do we use incidence matrix? When information about edges is more desirable than information about vertices. And then we normally use adjacency matrix if information about the vertices is more important than information about the edges. So I will just give an example for you to understand better the how to make an incidence matrix and and an adjacency matrix. So consider this graph here. Okay, so to create an incidence matrix, you just have to write all the vertices in a column, or you can put them in a row. So you have V, U, V, W in this case, or V, U, W. The order doesn't matter. And you have your edges E sub 1, E sub 2, and E sub 3. Now, you write 1 if the edge is incident to the vertex, and 0 if it's not. For example, E sub 1 is incident to V and U. Therefore, V E1 is 1, U E1 is 1. Now, E1 is not incident to vertex W. That is why it's 0 here. Another, E sub 2 is incident to both vertices U and W. So U E2 is 1 and W E2 is also 1. E2 is not incident to V, therefore V E2 is 0. Same with this. So this is now your incidence matrix. You can actually recover the graph by just looking at the incidence matrix. For adjacency matrix, example again, consider this graph here. So you just write the vertices in one column and same vertices in this row here. Next, um, we put 1 if two vertices are adjacent and 0 if they are not. For example, V is not adjacent to itself because there is no loop connecting V to itself. Therefore, V to V is 0. Now, V is adjacent to U. V is adjacent to U. Therefore, we put 1. Another, V is adjacent to W. So, since they are adjacent, it's 1. W is not adjacent to itself, so W is 0. W is adjacent to both U and V, so WV is 1, WU is 1. Okay, and here are the exercise. Please answer the following exercises. So you have four numbers. First is you draw a simple graph G with 6 vertices and 7 edges. And then you label the vertices with A, B up to F, and the edges with these numbers, 1, 2, 7. And then after which you determine the vertex set of G, you give the edge set, and then determine the vertices that are adjacent to vertex D, and so on. And for the second one, draw a complete graph of order 7, so K sub 7, K7. And then draw a cycle of order 8, that's C8, and then draw a complete bipartite graph. And that's it. Thank you for listening.